It's the mill room, and basically what we do is we take our crushed malted barley and then we go ahead and put it through the mill, grind it down, and it feeds up that auger line into the first vessel in the system. Basically once the grain is crushed, it's going to feed up the auger line, it's going to drop into this vessel here, which is known as the mash tun. When the grain is coming up the auger line, that little chimney, if you will, up top is called a hydrator. And so what happens is as the dry crushed grain comes in there, it hits a cone, it spreads out, and then there's a stream of hot water coming in. So it does essentially a pre-mixing of the grain in the water. We still use very high-tech ore to stir things up. It's got a 400,000 BTU burner underneath it. As you can see, the mash tun is fairly small compared to the boiler kettle. So what we do is, in order to make sure that we get all the sugar water out of there, which is what we're trying to do, we convert the starches to sugars, and then we're trying to get that sugar water, or that sugar into solution, and get it over into the boiler kettle. What we do with this little piping matrix is we actually create a little bit of a whirlpool in the kettle by pumping liquid off the bottom and shooting it in that tangential port. What that does, that whirlpool gets spinning in the kettle, it brings all the solids to the center of the liquid mass, and then we turn off the pump, and gravity takes over, so those solids actually drop out into the bottom of the kettle. The other thing that we do at exiting the heat exchanger is we actually inject a stream of medical grade breathing air into the wort stream. And what that does is that provides oxygen for the yeast that's waiting in the fermentation tank. And the reason that we do that is because when we put a yeast culture into the tank, it still has to build cell count. We want it to reproduce before it begins fermentation. You don't want enough yeast in there to start fermenting right away because we want a healthy yeast supply. We want it turning over continuously. So we'll put yeast in there, about a third, probably about 20% of what we actually need, and then we'll go ahead and we'll oxygenate our wort. As it goes in and mixes up with the yeast that's in the tank, that little lag phase while it's building cell count usually takes about 4 to 6 hours. Once that cell count, that sort of critical mass is reached, fermentation begins. And fermentation for beer is very simple. It's yeast consuming sugar and forming as byproducts alcohol and carbon dioxide. The other byproduct, if you will, that is formed is something called esters. Esters are fruity solvent-like aromas. To ferment, there's ale yeast and there's lager yeast. Ale yeast perform better at about 68 degrees Fahrenheit. Lager yeast are going to ferment better at about 50 degrees Fahrenheit. Both of those fermentations will produce esters, but the weird thing about lager yeast is, or the unusual thing, if you will, is their ability to reabsorb esters. So after primary fermentation, even though there's some fruity solvent-like aromas in the liquid mass, lager yeast actually reabsorb those as long as they're given sufficient contact time. They reabsorb those so that you don't get fruity characteristics in a finished When you're making beer, the basic concept is the more sugar, the more alcohol. And the more sugar you have, the more there is to ferment, the higher the alcohol content is going to be. Once fermentation is complete, we'll close the tanks down. The CO2 that's additionally produced will have nowhere to go. It will actually dissolve back into the beer. We use that method to carbonate our beers.
After visiting the Lafayette Brewing Company and learning about the various processes involved in beer brewing, we decided as one of the objectives for our project to model a semi-batch fermentation process. Other objectives include referring to previous studies for data and information, using the data information for data optimization, carrying out mass balances, looking into reaction kinetics for the fermentation process, varying process parameters, and to obtain the best product concentration, i.e. optimize the process.
As Greg mentioned in the video, fermentation is a process of converting glucose to alcohol and carbon dioxide. This is an enzyme-facilitated process, and the particular yeast strain that we decided to use based on literature we surveyed is called Saccharomyces cerevisiae. This is an anaerobic process, and the equation for this process is as follows.
For the analysis of our process, we took in consideration volume of the reactor, biomass concentration, substrate concentration, and product concentration. These variables were used below in our mass balances and are all time dependent.
As you saw in the previous slides, the process variables are dependent upon process parameters. The important process parameters that we took into consideration for the modeling purposes are biomass reaction rate, specific growth rate, rate of substrate consumption, rate of product formation, yield coefficient of the growth of biomass, and the product kinetic constants. These process parameters in turn are dependent upon the process variables. These are calculated using data from literature and the equations below. For modeling this process, we made certain assumptions for the system. We assumed that the system is quasi-steady state, the outlet flow equals 0, the process starts with a dilute solution of the substrate, and all variables are time dependent.
Temperature and pH are two important factors that affect the final product, which in this case is the beer. Not only does this affect the concentration, but also the flavor. Process parameters that depend on these two factors are mu, specific growth rate, KSP, the product constant, and YXS, the yield coefficient. Based on literature surveys and previous studies, the equations which incorporate the effects of temperature and pH are below.
Below is the model for our fermentation process. We have used published data, the Monod kinetics model, and MathCAD's ODE solver to help us best represent different situations involving fermentation.
Using the above equations and data, performance curves were generated, as shown on the slide. Of the many plots, the first observation that can be made is that the final product, i.e. the ethanol concentration, increases with increasing substrate, i.e. glucose concentration, which is the highest at an initial glucose concentration of 10%. Since we assume a quasi-steady state system, we also see that the biomass concentration increases exponentially. Theoretically, the biomass concentration is supposed to increase linearly as the substrate concentration begins to decrease and the product concentration begins to increase. It can also be observed that as the specific growth rate of the enzyme increases, the rate of biomass formation also increases. Having achieved a high enough ethanol concentration, we then look at optimal conditions in which this particular ethanol concentration can be achieved. So we pick the highest ethanol concentration. From this, we varied the temperature and pH as two factors, which could affect cell viability, i.e. the specific growth rate of the yeast strain, and the rate of the biomass formation. So the equations that were shown that could incorporate temperature and pH were used, and 3 different temperatures and pH values were used to produce the best combination and the highest ethanol concentration. The overall analysis shows that the highest ethanol concentration is produced at 10% initial substrate and at a temperature of 30 degrees C and pH 4. This is, however, only suggestive for this particular model and this strain of yeast, which is Saccharomyces cerevisiae. Other strains of yeast work under different conditions and could also be modeled in a similar manner.
Wait, so what are you going to ask me then?
So Rob, do you like beer?
Yes, I like beer.
Okay, what do you look for when selecting a beer?
I look for a strong, hoppy taste.
Okay. Is alcohol content important to you?
Somewhat.
Do you like drinking beer?
No.
What do you look for when selecting a beer?
Well, I look for A, the color. I buy the most expensive beer always, because I'm rich, and whatever has the most hops.
Drew! Do you like beer?
No.
No?
No.
I like just taping you.
Well, now that you've turned 21 and can drink, what do you look for when ordering a beer?
Cheapness?
Cheapness? Alcohol content?
Oh, high preferably.
Okay. Flavor? Do you like bitter or sweet?
A manly beer.